Here are some notes for you for section 3.1. We'll call this part 1. You could separate this section into two parts. The first part is really more of a conceptual sort of why we are going to be interested in the kind of problem we're going to be interested in here, and then the second part kind of gets more into the nitty-gritty of that. So part 1, we want to talk about the concepts of average velocity and instantaneous velocity. Instantaneous, there you go, velocity. If you're thinking maybe I've lost the plot here and I'm accidentally talking about physics class instead of calculus, well, these are physics kind of ideas, but the whole, the birth of calculus, the invention of calculus, came about or happened because of problems that needed to be solved in physics. So our motivating example for why we're going to talk about the things we're going to talk about in Chapter 3 does come from physics. So you might think slight advantage to physics students, but I don't think it's pretty basic stuff that we want to think about. Okay, so let's think about an example. Let's say you leave Lexington at noon and you arrive in Harrisonburg at 1 o'clock. And from Lexington to Harrisonburg, it's just about, it's about 60 miles. So let's say, well, we'll do the mile markers. We'll say, so let's say you get on here at mile marker 191. And that's where you get on the highway leaving Lexington. And then you get to Harrisonburg at mile marker 247. So what can we say about this situation? Well, we can talk about what your average velocity is. The definition of velocity is some distance traveled divided by the amount of time that it took, right? And if you want to know average velocity, then the definition of that is it's exactly this. So we can spell it out if we want to. It's your final position. So I'm going to call that position x final minus x initial. So the difference between where you ended and where you started, that's the distance, or it's your displacement, but we'll get into that difference later. And then the time, this is the time final minus time initial. So here, our average velocity is, in this example, equal to, let's see, how far did we go? We went 247 minus 191 miles, and 1 p.m. minus 12 p.m., assuming we haven't gone all the way around the clock, is 1 hour. So that would be, what, 56 miles in 1 hour. So our average velocity is, if you want, that's fine. You could say 56 miles per hour if you like to write it that way. There you go. Okay, now what else can we say? What if I asked you right at the instant at 12:30 p.m., when you're halfway, measuring by time, when you're halfway at 12:30 p.m., how fast are you going then? What can you tell me about that? And the answer is, given this information, you can't say anything about that at all. We don't know. All we can say is that the average was 56 miles per hour. I don't know how fast. You could have been going 56 miles per hour right there, but you could have been going faster then, or slower, right? You could have hit a little bit of traffic right at that moment, or you could have been speeding right at that moment. Who knows? So we could probably guess that the speed wasn't exactly 56 miles per hour the entire time. It probably fluctuated. Sometimes it was higher, sometimes it was lower. So what if we want to actually talk about that instantaneous velocity? How fast is something going right at that instant? Well, let me point out here that your average velocity looks like a x minus x over t minus t. That looks an awful lot like slope. And it is, right? It is slope if we're looking at a graph of position, x, versus time. Then x minus x, well, that would be the rise, and t minus t, that would be the run. So this expression here is a slope expression if we're looking at a position versus time graph. So, well, that's interesting. So what if we do look at a position versus time graph? So here's another example. I'm not going to bother scaling those axes. I'm just going to leave it like this, and we'll just talk about what we think might be going on. So what do you think is going on? What would we do if we wanted to find, how would we find the average, let's say, let me just put a, instead of an arrow there, let me just put a point there. And let's call this, we'll call this time 0 here at the start, and we'll call this time 1. And we'll call this, that's position 0. Looks like it is 0. And then we'll call this position 1. So at time 0, it's right here at position 0. And sometime later at time 1, it's up here at that position. So if we wanted to find the average velocity, we do this, right? We use this little formula here. And if you want a visual on that, what we're finding the slope of this line. If we're finding the average velocity, that is the slope of this line that connects 2 points. I don't know if you remember this from geometry or if you even have ever used this word in this way, but I think you have, maybe when you studied circles in geometry, a line that connects 2 points and keeps going through. It's not a chord, but one that keeps going. It's called a secant line, and we use that same vocabulary here in calculus. So the average velocity is the slope of this secant line. And the expression for that, why not write it again? Because we're just getting used to this. So it's this. It's just the slope formula, right? Sorry, those are I's, not ones. Okay, what if we wanted to know the instantaneous velocity? Well, we could extend this idea. We understand that velocity is slope. So if we wanted to know the instantaneous velocity, here's one way that we can approach that problem. I'm going to redraw my graph so I have a little bit more room to work and mark it up. So here's a similar graph, and let's say I want the instantaneous velocity at time 1. Actually, let's call this time 0, at t sub 0. just some fixed time, some arbitrary time. I want to know how fast things are going there, how fast this, whatever this represents, whatever this graph represents, I want to know how fast is that thing going right at that instant. So instantaneous velocity is, you can kind of imagine like if you're driving down the interstate and you want to know how fast you're going, you just happen to glance at the speedometer and it gives you a number. You don't have to wait until you drive an entire mile. You don't have to wait until you drive half a mile. You don't have to wait until you drive any distance at all. You can just look at the speedometer and it tells you a speed, right? That's how fast you're going right at that instant. So that's what we'd like to know. Now the problem here is to find velocity. Velocity is some distance that we've traveled over some expired time. And if you want to know right at an instant, then no distance has been covered in 0 elapsed time. So it's almost like you're trying to find slope with one point. Now that's a little bit tricky. So we need to think about this carefully and see if there isn't a way of defining this. If you're thinking, well, maybe it's just slope, it's just the slope at that point. You're exactly right. The question is, how do we actually find and define what that slope is? And here is one way to do it. So I'm going to pick another arbitrary point, T1, but we're going to let this point slide around. I'll call it slider, why not? And we can, of course, say the average velocity, that's the slope of the secant line, it's x1 minus x sub 0 over t1 minus t sub 0, right? If you want to mark these over here, those are just the positions that go with those times. Right? So it's just the slope. Okay, that's fine. But that's an average velocity. We want instantaneous. We want the velocity right here. Well, here's a trick. What if we took this point and kept sliding it closer and closer and closer and closer and closer to that point? We could get better and better and better and better approximations of what that instantaneous velocity was, right? As t1 got closer and closer and closer to t0. Right? Of course, when it actually gets there, well, then this would be 0, and this would be 0 too. It would be 0 over 0, and maybe that makes us think about limits. And in fact, that's exactly how we are going to define this, that the instantaneous velocity at time at t sub 0 is equal to the limit as, now what are we doing here? We're letting this t1 get closer and closer to t2 to t0, right? T1 is sliding closer and closer and closer to t0. So t1 is approaching t0. And what are we taking the limit of? We're just taking the limit of the slope. x1 minus x0, t1 minus t0. And what happens is it gets closer and closer and closer. We get closer and closer and closer to having the slope of the tangent line. So instantaneous velocity is the slope of the tangent line. You remember that what that means from geometry? It means that's the special line that just barely touches it at one point. It just grazes that. If you tilt this even the tiniest bit either way, it will hit more points. But there's a special slope there where it just grazes that and only manages to go through one point. That is the slope of the tangent line. How do you find it? We can find it using limits. And we define that instantaneous velocity. It's the slope of the tangent line. How do you find the slope of the tangent line? You set up a secant line and you let this point slide closer and closer, like so. So in the book, you're going to try some problems where you're going to be looking at some graphs and thinking about instantaneous velocity and average velocity. So I'm just going to give you one more example. make up a graph here, and maybe we can talk about some of the features of it. And I apologize if I make one that ends up looking an awfully lot like one of your homework problems. So let's see. Let's try that. And let's make some points on here. Let's say this is point A, B, C, and D. Okay, I might mark this up a little bit. So how about average velocity from A to D? So as this thing moves, and let me just also make the point here that what we're looking here is something that's moving back and forth in one dimension. It's not actually moving on a curve like this. This is the time dimension. This is what's happening as time unfolds. So this is something, if you imagine a number line here, something that starts at point A here, and then it moves backward this way toward point B, then moves back some more to point C, and then turns around and goes back at point D. And D, of course, is in the same place that B is, right? If you look at those, they're at the same location. So this is something that's moving back and forth in a line. It's stretched out over time, which gives it the appearance of a curve, and it's a very, very useful way for us to look at it. If I just look at this number line with A, B's, and C's and D's on it, I can't tell what happened, right? I could try to put some times on there, but this is a much more convenient, and much more, I think, information-rich way for us to look at this. All right, so what's the average velocity from A to D? Well, I didn't put any numbers in here, but the average velocity is the slope of the secant line. So the secant line from A to D, it's definitely negative. Right? How about the average velocity from B to D? Well, the slope of this secant line, average velocity from here to here, that's just 0, right? And that makes sense. If you leave Lexington and you drive to Stanton and then you come back to Lexington, the average velocity for your whole trip is 0 because the difference between the position where you start and the position where you end is 0. It's the same. You're in the same place. There is something else called average speed, which we can talk about some more, and we will talk about some more later. And that wouldn't be 0. That's the total distance you covered divided by the time. But if you only are talking about velocity, that's just your the difference in your positions. In other words, your displacement divided by time. And you know what? Let me go back to this for a second. I should really say here. I said distance here. That really should be displacement. Right? Speed is distance over time. Velocity is displacement over time. That's a subtle difference, but it's very important. It's important for us. It's important in physics, even more so. So I apologize for that. I go back and fix that, please. All right, so the average velocity from B to D, since B and D are actually the same location there, it's 0. Right? How about the instantaneous? When I say instantaneous velocity, I'll just say like V sub B. So what's the velocity right at B? Well, here, that would be the slope of this tangent line. So can you picture that? A line that's going right in the same direction. Sometimes I describe it to students, if you could imagine a tiny little car driving on this road, when it's right there, it's the direction the headlights are pointing in. It'd be that line that the headlights made. If they were like laser pointers, you can go forward and backwards. That's the direction of the tangent line. So it's definitely negative. And greater than, it's in absolute value, it's steeper than this was, right? So right here, you could say it's going faster in the negative direction, right? It's steeper. Steeper means faster. So it's a bigger negative number. So you can make a comment there about that if you want. How about the velocity at A? A, it looks like, looks like actually the tangent line would be pretty close to 0 there. And how about at C? The instantaneous velocity at C, a tangent line there, also looks like would be 0. And it is true, something that will be of great interest to us, that at a maximum or a minimum point, so long as there's not a sharp corner there, at a maximum or minimum point, we do in fact get a slope of 0. So that instantaneous velocity would be 0 there, and then C to D, D would be positive. And the average velocity between C and D would also be positive, but it would be less than this, right? The instantaneous velocity of D at D is greater. So here we're going from C to D, so it looks like from C to D, we're going from having a velocity of 0 to having a velocity of some positive, so we could say that it's speeding up. The velocity is increasing. And then last thing, and this one I think deserves some careful thought on your part. So from A to B, we're going from 0, from a velocity of 0, to having some kind of negative velocity here. Is that speeding up or slowing down? Think about that for a minute. Well, if at A its velocity is 0, that means it's not moving, right? So if you go from not moving to moving, that's speeding up, right? In this particular case, it just so happens that we're speeding up in the negative direction. But speed, if you get on the Interstate 81, and you set your cruise control at 70 miles an hour, because you're a law-abiding citizen and you wouldn't drive faster than that, you're going 70 miles an hour, right? Now, let's say we just make a decision here that north is the positive direction and south is the negative direction. You could say, and it would be perfectly correct to say, that when you're driving north on Interstate 80 with your cruise control, 81 with your cruise control on, that your velocity is 70 miles an hour positive when you're going north and 70 miles an hour negative when you're going south. But the speedometer in your car, which is a speedometer, it's not a velocity meter, it's a speedometer. It tells you what the speed of your car is. It does not care about that direction, right? So here, how does that play into this example? Here the speed is 0, and here the speed is whatever the absolute value of this slope is. Speed is the absolute value, it's just the magnitude of this. So we're going from 0 to moving. So from A to B, we are speeding up. But what's happening to the velocity? When we talk about velocity, we care about the sign. It's going from 0 to a negative slope. So the velocity is actually decreasing. It's getting further into the negatives. So that's something to think about, right? It's important to understand that difference between speed and velocity, something that will be very important, again, even more important in physics, but very important for us in calculus too. So there's some things to think about. That should put you in good shape to do the first 8 problems in section 3.1.